Hello everyone, thank you for joining us for today's 17th webinar. Today we have Esra Capanoglu from Turkey and she will give us the presentation about enhancing bee products functionality via encapsulation strategies. I'm eager to hear more about it. And dear Esra, the floor is all yours. You can give us your presentation. You're just muted, by the way.
Oops. Can you hear me now?
Yes.
Okay, yeah. So now, first of all, thank you very much for the kind introduction. It's a great pleasure to be presenting here today. So I'm very happy to be involved in such a great consortium within this cost action. And of course, as all of us, I have been following all the activities, and it's very nice to be involved in such an active group. So now, today I will be talking about the effect of encapsulation, how to protect the bioactive components that are highly present in bee products. So I will try to present some data of our group. So now I'll be sharing my screen. Yeah, so I'm sorry. So I'm at the airport and I hope there will be no problems with respect to connection, but yeah, I will do my best. So I think, yeah. Yes, I think you can see my slides, right?
Yes.
So once again, thank you very much for the kind introduction. I'm Esra Capanoglu from Istanbul Technical University Food Engineering Department, and we have been working on the bioactive properties, bioaccessibility, and bioactivity of different bee products for a while. And today, I will be focusing more on the effect of encapsulation, how it may protect the bioactivity of these products. And of course, first, I will try to give you a short introduction. So, of course, as we all know, bee products have a high potential in terms of their bioactivity and bioactive properties. So I think it's not necessary to mention, but we know that there are several flavonoids, organic acids, phenolic compounds that are present in these bee products and which are associated with the antioxidant, antimicrobial, or anti-inflammatory activities of these components. So we know that there are several bee products, but at the beginning, before passing to the encapsulation part, there's something that I would like to mention, which is related with the variability of the components or the contents of these products that are available in the market, which is quite critical, I think, from our point of view. So we know that we have honey, bee pollen, royal jelly, bee bread, or propolis that are all available in the market. That's the same for the Turkish market as well. So we know that as we have gathered some, I will be showing you a product, I will show you a paper related with this work actually. So we have collected some samples from the market and we observed that unfortunately due to mislabeling or due to some problems in labeling of these products, so unfortunately we were not able to obtain what it was written on the label. So before going through the encapsulation issues, I will first try to focus on the differences between the components or the composition of these products which are available in the market. So we know already that all these bee products have a high variability because of course, differences in their origin, geographical location, climate differences, or bee species, etc. So it means that already we have a certain raw material that's variable due to its natural composition. And we know that, of course, there are several different products available in the market, and they are composed of different bee products. And unfortunately, as I have mentioned, these are not standardized in most cases, so which is an important issue. So I will show you this paper that we have published very recently. In this work, we have collected several samples, especially liquid propolis products, gathered from different countries. And the thing that we have encountered was that, unfortunately, what we have obtained was that not all these products were containing sufficient levels of bioactives. So even though when you read the label, it is indicated that it contains high levels of propolis or any type of bee products. Unfortunately, when we have investigated, when we search for the bioactive composition of these products and their antioxidant potential, what we have observed was that it was much lower than what we have expected. So this indicated us that, of course, one of the main issues that we encounter with the commercially available products is that, unfortunately, they are not really standardized. They don't have a clear labeling. So also in most cases, unfortunately, there are some problems with respect to regulated issues because it changes from one country to another. So all these create some problems at the end. So as you see here, so the different samples that we have collected from different countries, and on the right hand side, you can see the demonstration of the scientific data that we have obtained. And it is quite variable between each other, indicating that, as I have mentioned, the standardization of the product is a necessity. So if I come to the other challenges that are associated with products, unfortunately, the compounds, flavonoids in most cases, not only for the products, but also for other natural components, fruits and vegetables, or other products as well. Unfortunately, they are not very stable. So they are affected by, in terms of pH, in terms of light, oxygen, presence of other components, etc. So they are not really highly stable. And the second problem is with respect to their solubility, as we all know, because probably we have all tried to implement these components or compounds into different food matrices. And at that point, we have encountered some problems with respect to their solubility, because if you are able to, or if you try to incorporate them into aqueous food matrices, we come across with several problems. And of course, another important challenge is the unpleasant taste of these compounds. Unfortunately, for example, especially some components like propolis, they have a very strong taste and flavor, so it makes things difficult for their use and for their incorporation into different matrices. Another problem is related with their bioavailability, bioaccessibility, and of course their stability throughout the gastrointestinal digestion or tract, because we know that, of course, all these bioactive components come together with the gastric conditions and several different enzymes during digestion, and they can be degraded into different components which are not really very stable. And finally, from the allergy and safety point of view, we know that unfortunately, some of the products may create some allergies. And of course, related to those, unfortunately,
Sorry, Esra, there is some background noise. We can't hear you well.
you cannot hear me well. Yeah. So, yeah, probably there's an announcement and it's due to this, but I will try to make it louder. So, can you hear me now clearly? Is it better? Because probably it's because of the noise at the back. We recommend that you deliver your baggage to the boarding agents or still facilitate your boarding and deboarding process. No fee will be charged for delivered standard cabin baggage. So shall I continue, or do I need to wait for a while? Please ensure that your baggage does not power banks, electronic cigarettes, or I hope you can hear me.
And remember to take any items you may need during the flight with you.
Okay. So yeah, another problem is that not properly. So yeah, I will try to speak a bit louder. Okay. So I hope it's better now. So yeah, the last point is, as I have mentioned, is the allergic reactions that we may come across with the bee products, and of course the safety issues, especially which is directly related with the concentration of these products. So if we come to the impact of encapsulation, so I have already named several challenges that we may come across with. And of course, encapsulation could be a good strategy in order to avoid or let us help to overcome all these challenges. Because nowadays, because of these biological or technological limitations of bee products that I have named, it could be a good option to provide protection for the bioactive components that are present. So what we can achieve by means of encapsulation is that, first of all, they can provide better solubility. And of course, for example, for the components which are not dissolved, which are not able to be dissolved in aqueous medium or vice versa in lipophilic medium, it could be possible to achieve to solubilize these components in different food matrices. So this is the first advantage that encapsulation may provide us. The second one is, by the help of encapsulation, we are able to mask the off flavors and the taste, the bad flavors that we don't like to have in several different bee products. For example, as in the case of propolis. So with the help of encapsulation, we can mask this undesirable taste, which is also very important. And of course, with the help of encapsulation again, we are able to improve and increase bioavailability and bioaccessibility, and we may provide a better controlled release. And by this way, of course, we may obtain better functional characteristics and bioactive properties, and they can be also implemented into different food matrices. So these are the advantages that the encapsulation may provide. So, of course, meanwhile, while talking about safety, the reduced toxicity with the help of encapsulation is another advantage that can be provided. So now I will try to give you some specific examples of the work that we have been performing in our laboratories related with the encapsulation of different types of bee products. So, as you all know, one of the most important parameters for encapsulation is the methods that you use, and of course, and the raw materials and the concentration of these raw material and the core material ratios, etc. So it means that there are several parameters that we need to optimize to go further with these encapsulation techniques. So what we have done in different work is that we try to optimize several methods of encapsulation, finding out some novel or new encapsulating materials. For example, you know that maltodextrin is one of the most widely used material as a wall material for encapsulating different bioactives. But lately, beta-cyclodextrin, for example, has been started to be used, and actually it has been previously used for some medicinal purposes or encapsulating different bioactive components. But in this case, we try to use it for the bee product, and actually we have obtained quite good results. So in this work, so we were trying to investigate the effect of beta-cyclodextrin encapsulation and to see its potential, whether it can be used for encapsulating bee products or not. So what happens here is that the encapsulation, of course, you know that, again, the people who have been working with encapsulation knows quite well that there are several parameters to be investigated to see whether the encapsulation efficiency is good or not, if it is sufficient or not. So for the encapsulation, we of course measure or characterize the samples or the particles that we obtain. For example, we measure their particle size, we measure their zeta potential, because zeta potential is also a good indicator of showing the stability of the complexes and the repulsion between the particles and these complexes. So we have investigated also the zeta potential of these components, and what we have obtained was that at the end, actually, we have tried different ratios of these, the extract and the beta-cyclodextrin complexes, and we have found out that 1:2 ratio yielded with the best results, yielding an encapsulation efficiency of 64%. So, what we have done afterwards is we have investigated their antioxidant and antimicrobial potential, because we know that these components have good bioactivity. So it means that one of the targets, one of our aims was to see what will be the performance in terms of antimicrobial and antioxidant activity. So the results indicated that these complexes had a lower level of antimicrobial activity compared to the original samples, because they showed really strong antibacterial activity. And in case of encapsulation, we observed a modest reduction. However, we observed on the other side, an enhanced bioaccessibility of these components. For example, in terms of their antioxidant capacity, in terms of their phenolic content, all the bioaccessibility values were improved by the effect of encapsulation. So it means that we were able to obtain better results in terms of the bioaccessibility of these bioactive compounds. So I will now switch to another work, another study, in which we used a different technique where the supercritical antisolvent processing was applied. So this part was applied for the encapsulation, for producing micro and nano-sized particles by getting use of carbon dioxide under supercritical conditions. So this is a more like a novel technique for that can be used for processing or for producing these particles. And afterwards, after the production of these particles, we have also investigated what may happen to these components and to their bioactivity when they are applied in different food simulants. So these food simulants have been selected. These are because the already published simulant, for example, 3% of acetic acid mimics acidic foods, 10% of ethanol mimics low alcoholic beverages or aqueous foods, and 50% ethanol is a good environment stimulant for the lipophilic food. So these are all selected by the legislations that have been published by EU. So what we have observed was that actually we have just let them gone through digestion, and we try to observe what happens to the phenolic content, flavonoids, or their antioxidant capacity as a result of these encapsulated components, particles in different stimulants. So we observed that the highest encapsulation efficiency was reached at 75% under the conditions of 40 Celsius and 150 bar. So these were the best results that we have obtained. And of course, when we compare different stimulants, for example, the lipophilic stimulants and what happens to in an acidic environment, when we have compared them, we obtained the results that the lipophilic stimulants showed the highest bioaccessibility values, which makes sense because we know that it has been already indicated in the literature that lipids may enhance the bioavailability of certain bioactive compounds by protecting them or by providing a layer surrounding them, which may lead to their better or protective passage through gastrointestinal tract. So it was something that we have expected already considering the literature background. So it means that the lipophilic food stimulants showed a good result. So in another study, we have investigated the liposomal encapsulation of, this time we worked with propolis, and we tried to investigate ultrasonication-enabled propolis extract. So we have investigated the bioaccessibility, bioavailability, and food application. So this time, the hydrophobic propolis is the extract core, and the kilogram is the outer shell, and in between we had lecithin. So we had like a double layer, so the bilayer. So what we have obtained according to the results of this work is that the ultrasonication treated liposomes were better compared to when we didn't apply ultrasonication. So it provided or it enhanced the stability of these phenolic compounds in propolis extract, and our efficiency was something between 53 to 76. And the highest efficiency was obtained, as you can see, with a propolis concentration of 0.05. So at the lowest concentration, we were able to encapsulate it in a better way. And of course, we have done all the characterization assays, all the characterization analysis, like the zeta potential. For example, it's also good to indicate that normally the primary liposomes provides a negative zeta potential. However, it is being converted into a positive zeta potential when the second layer with chitosan is coated. So similarly, of course, the results indicated that the 0.5 this time, so of course, the ones that contains higher levels of propolis showed better results or higher values of antioxidant capacity of phenolic compounds as expected, because of course, as we increase the level or the amount of the components, the major material, which is propolis in this case, of course, we obtained better results. So one of the main ideas in our studies is also to observe what happens in different food matrices. So this is one of our targets or aims to see in applying these materials, these functional ingredients into different foods, what happens. So in most cases, we add these components as raw directly itself. And of course, we have also tried to involve these components in their encapsulated forms, and we try to compare the effect of encapsulation. So in this case, we used apple juice, and we tried to produce apple juice which are enriched with liposomes, which contains high levels of bioactive compounds, as you have seen in the previous slide. So, and we try to investigate what happens in terms of their bioaccessibility. So as you can see here, the secondary liposomes together with the apple juice. So when the secondary liposomes are included in the juice, it yielded the highest values in terms of bioaccessibility. So it means that normally we know that apple juice is highly hydrophilic and it has a low pH, but even under these conditions, the secondary liposomes worked quite well when we have included 10% of propolis-loaded liposomes in apple juice. So similarly, the bioavailability results were also in parallel, indicating that, again, the ones that are loaded with 0.5% of propolis, these secondary liposomes, contains quite good total phenolic contents and antioxidant capacity, and the bioavailability. So the initial value and both the bioavailability of these components or of these antioxidants were quite well under these conditions. So in another study where we tried to investigate the effects of different homogenization methods after encapsulation. So one of them was microfluidization and the other one was ultrasonication. So here again, we have prepared secondary liposomes of bee pollens, and we try to investigate their stability and bioavailability. What happens if we treat them or if we homogenize them by getting use of different techniques. And of course, these parameters have been investigated in advance with some prior applications or treatments, and also, of course, checking the literature. And we have applied both microfluidization and ultrasonication. So the idea was to compare these two methods and, of course, to obtain efficient encapsulation at the end. And we have, of course, we have investigated their particle size. We have compared the encapsulation efficiency by using these two techniques. And the results indicated that the liposomal encapsulation, which are homogenized by means of ultrasonication, yielded with better results. So it means that in terms of or compared to microfluidization, ultrasonication was found to a better result for the homogenization of these particles. And as you can see here, 0.4% of the involvement of these components of the pollen extract yielded with the best results, even during the different stages of digestion. 0.4% of pollen extract involvement yielded with the best results at any stage, and also by using any techniques that are available. So, similarly, in terms of bioaccessibility and bioavailability, similar to the initial values, again, we obtained the best results by 0.4% of pollen extract loaded secondary liposomes. So it means that in terms of the use of liposomes, the secondary liposomes yielded with better results, and ultrasonication again yielded better results. And this was the case both for bioaccessibility, as you can see on the left panel A and B, and for the bioavailability as well that we have investigated by using TECO2 cells. So on C, you can clearly see that still we obtained good results in terms of bioavailable particles. So as I have mentioned at the beginning, so one of our targets have always been to investigate the effect of different food matrices. So not only creating or producing these capsules or these particles, but also to observe their changes, their effects or their interactions within different food matrices was another idea. So here in this case, this time we tried a different matrix, like a bread matrix, a bakery product. And we observed that at a percentage of 10%, incorporation of these liposomes that we have obtained at the first stage yielded with a very good results in terms of nutritional profile, in terms of both phenolic contents and antioxidant capacity, as you can see at the upper panel, and also both for their bioaccessibility that you can observe at B and the bioavailability that you can observe at C. We observed quite well results, so we concluded that the incorporation of 10% of these liposomes, which includes 0.4% of pollen extract, yielded with quite good values. But of course, the further stages should be investigating their sensory attributes or the consumer acceptance, etc. So there's still some time or some work that needs to be done. So the last work that we have performed was related with the royal jelly this time. And we have incorporated this into kefir samples, which are also, became very popular last years in terms of their health effects. So here we observed that these are the empty liposomes on the left-hand side, and the royal jelly-loaded liposomes worked quite well and sufficiently and effectively. We were able to encapsulate these royal jelly samples. And of course, again, we used these two steps of liposome formation. So the first one was using lecithin-based primary liposomes, and the second one was coated with chitosan to form the secondary liposomes. And actually, we yielded with good results, I can say. So the encapsulation efficiency, especially with the use of 0.5% of royal jelly, was yielded with quite high values in terms of encapsulation efficiency. So you all know that encapsulation efficiency cannot yield with very high values, unfortunately. So they also have certain limitations. Maybe we can discuss them later within a different webinar. But of course, still 60%, 70, 80% of encapsulation efficiencies, especially with matrices that are so complex, like the royal jelly, propolis, etc., are accepted as good. So we have also characterized the structures of these bioactive components by getting use of measuring their particle size, the potential, etc. And at the end, the encapsulation efficiency values ranged from 48% to 63% approximately, and with the use of 0.5% of royal jelly, because you know that the inclusion levels of these components are also another critical issue. So here, as you can see again, with the inclusion of 1.5% royal jelly in this case, this is again similar to what we have obtained in the previous work, because as we increase the content of royal jelly in our samples, of course, the antioxidant potential or the phenolic content increases as expected, for sure. And in this case, actually, the bioactive properties of liposomes were very positively influenced by the presence of royal jelly concentration, and throughout the whole digestion stages, it was the same case. So 1.5 royal jelly yielded with the best results. So what happened when we have applied them in kefir samples? So if we apply them in a different food matrix like kefir, what happens? As you can see on this table, the kefir and the liposome samples yielded with the highest results in the intestinal phase. So indicating that the royal jelly inclusion was actually was protected in forms of the liposome, because it was higher compared to the royal jelly inclusion itself. So it was the liposome incorporation or the incorporation of royal jelly in forms of liposomes, let's say, yielded with better results. So when we have a look at the bioaccessibility and bioavailability values, of course, we observed an enhanced bioaccessibility with the use of these liposomes, because they have protected the bioactive compounds that are present in royal jelly. And of course, after Keiko-2 cell application, which indicates us the bioavailability, so still we had an absorption rate of 51% and with a high antioxidant bioavailability. So now I would like to conclude that we all know that bee products are promising and they contain good sources of bioactive compounds which may show antioxidant, antimicrobial, or some other health promoting potential. So it means that we have a good potential by getting use of these bee products. However, in order to get rid of some challenges that I have mentioned at the beginning, for example, solubility issues, standardization issues, so we need to take care actually, because we know that due to these changes in the depending on the variety of the products that we use, also depending on the geographical location, climate, etc., our raw materials are already quite variable, and also unfortunately they are not stable. So due to this nature of these components, we need to consider of some novel technologies or systems in order to improve their technical and functional properties. So encapsulation could be a good option in this way. So in order to improve the solubility, bioavailability, or bioaccessibility of these products, and also masking these unpleasant sensory properties, we can again get use of encapsulation. So within the work that I have shared with you, this chitosan coated secondary liposomes show the good potential. So it means that they can be really used for a good alternative in terms of encapsulation methods. And of course, we always need to investigate the further steps, meaning that the food applications are also quite critical, because otherwise we are not able to really fully understand the potential of these components as functional ingredients, because of course they can be consumed alone or directly, but if we would like to improve their usage, we need to go further for other applications. So for example, for food applications, for nutraceutical applications, we need to find new approaches. So it means that in short, these components or these products can be accepted as a next generation functional food, considering their high potential. And of course, we can tick off how they can be improved or how they can become more widespread throughout or during our diet. So finally, I would like to show you our Marie Curie staff exchange project, which is also directly relevant to this topic. So the acronym of this project is BTech, and the open form is Biotechnological Development of Bee Products for Sustainable and Functional Foods in Healthy Aging. So this is being coordinated by us, by ITU, and the main idea here is to obtain the better, more sustainable and functional food ingredients from these bee products, and just to increase their application potential. So we will be working with propolis, bee pollen, royal jelly, and bee bread. And we have different partners from different countries like Turkey, Germany, and Romania. And I hope that we will be also able to collaborate through this project all together. So thank you very much for your attention and for your time. And I hope the quality of the voice was not that bad, and it was you were able to understand. So thank you very much.
Thank you, Esra, for your presentation. I myself, not a chemist, so I don't have any specific questions, but if there is somebody in the audience who would like to ask something, please do. Okay, we have messages of thank you, but I don't think anybody has questions right now. So even if you do, you can always email Esra for additional information.
Yeah, definitely. So you can find my email address on the website of Istanbul Technical University. So I would be always very happy to answer your questions if you have, or anything that we can collaborate, any projects or any work. So we will be happy to be collaborating with you all. Thank you very much. Thank you.
Thank you, everyone. Then see you next month for next webinar.